Okay, so thank you everyone for coming. Today I will be giving, this will be like a rather short talk. I'm gonna go straight to the point, talk more or less about the theorem, what are the ideas and the tools without going into the technical details. So what I want to talk about today is exactly written here. We're going to talk about common tangents to convex bodies. This is joint work with Joseph Doolittle in TU Graz right now, a postdoc, and Jose Samper, which is another colleague, professor in Chile. And this is based on some preprint that is up in the archive today. So this is the first time that, so this appeared a couple of hours ago, and now I'm talking about it. So we used to have a different version, and I'm going to talk briefly about why we have different versions, and this version with convex bodies appeared this morning. Okay, so what is the point here is we're going to talk about tangents. Tangents are what you think they are, and convex bodies that we will have to briefly define. But the story here begins 2000 years ago, when you have a problem of having these two circles. And let's say that the circles are disjoint, and we want to draw the tangent lines to these circles. So this is well known that we have 4 tangent lines. Now here I draw the tangent lines in blue. Of course, without precision, I just try to draw some lines. But you can see that if the circles are perfect and the lines are perfect, there are still 4 perfect lines that will be tangent to both of them. But how to find these lines? This thing, the Greeks already had a concrete construction. They didn't have, or well, in general, they did have, but in this case, their proof was not an existence proof. It was effective. They had an algorithm with ruler and compass that you can produce these lines. I invite you to think briefly on this problem. It's not trivial, it's not super hard either, but it's definitely a lot of steps to build these 4 tangent lines. And it's not easy, but it's not too hard, and it's a nice problem to give a high schooler. And keep in mind that it is important for these 4 tangents to exist that the circles are disjoint. You could have other crazy situations in which there is only, let's say, there could be no tangent lines. If you have one circle inside of the other one, then there will be 0 tangent lines. You could also have 1 tangent line if they are nested like this. You could have 3 tangent lines if they touch outside, so there will be like a unique one separating them. But if they are disjoint, we know that there are 4, okay? And this is the basic result that we want to expand, okay? So let's try to see how a statement like this may look in 3 dimensions. So we go to 3D, and let's imagine that we have this picture. Of course, this is a cartoon, but you get the idea. So this is 3 centers. Let's say that they are all in the same line. And I have 3 spheres, 3 balls, one here. The one in the middle, let's say that is a smaller, and then a large one, let's say equal to this one. These 2 are equal, and this is a different one. So in this case, we have 3 disjoint balls. So how many tangents do we have? Well, you think about it, if these 2 guys have like a larger radius than this one, there are no tangent lines, so 0 tangents. Okay, even though they are disjoint. Okay, that's kind of complicated. And let me show you another example. This example is more artificial, but it shows also what can go wrong. So let's put a ball here. Let's put a center, the center, the center. So let's put a ball here of, let's say, radius 1, and I put here another ball of radius 1. And in between them, I'm going to put in a sphere of radius 1, I'm going to choose 5 points, which is a pentagon. And to make it 3-dimensional, I'm just going to make a pyramid somewhere. And let's say that these centers are aligned. So if I do it in a way that the circles, like these projections, are all the same, then how many tangent lines do I have? Well, I can produce a tangent line, a tangent hyperplane here, tangent hyperplane. Oh, I am changing lines by hyperplanes in this case. Then here I will have another tangent hyperplane. And here I will have another tangent hyperplane, and here and here. So I can have 5 tangent hyperplanes. I can have 0 tangent hyperplanes. And this construction here, there is nothing special about 5. I can force this thing to have n tangent hyperplanes. So naively, if I just say, give me 3 convex bodies, why 3? Well, in this example, I'm just saying 3 convex bodies that are disjoint. They can have apparently any number of common tangents. Okay, which is in contrast to the example in dimension 2, where in dimension 2, with 2 convex bodies, we simply have 4. If they are disjoint, they will have 4. They don't have to be circles, right? They could be like a square and a triangle, and still you will be able to find these 4 tangent lines. Okay, so there is something weird here. The conclusion from this example is that I cannot naively generalize disjoint to disjoint. I cannot just add more convex bodies in higher dimension and ask them to be disjoint. I have to ask for something else. So let's first do some definitions. So what do we mean by, say, a convex set? So a convex set, well, we all know what is a convex set. Simply, if I have any 2 points inside, I request that if I have a point here and a point here, I want the straight line, let me make this a straight line, to be contained in the set. Okay, we all know that. Now, what is a strictly convex set? A strictly convex set is one that in the boundary of your convex set, you have a unique tangent, a unique tangent hyperplane. A tangent hyperplane is what you think it is. It will be a hyperplane that intersects the set, and it has the whole set on one of the half spaces, closed half spaces. Okay. So in this case, being a strict convex body means that if I draw this tangent line, so again, this is tangent. Why? Because it intersects the convex body, and the convex body lies completely on this closed half space. And you are strictly convex if at any point in the boundary, there is a unique tangent hyperplane. So of course, the typical example here will be something round like a circle, a sphere will have at any point in the boundary, there is a unique tangent hyperplane. Something that is a non-example are obviously polytopes. So if you have something like a triangle, okay, in this triangle, you have several, for example, at this point, this is a point in the boundary of the set. The set is convex, yes. Is it strictly convex? No, because you can draw several tangent lines, tangent hyperplanes. So this thing will not be strictly convex, not strictly convex. And this will be, well, I mean, you have to draw it precisely. Of course, this is an ugly drawing that may not even be convex, but this is, assuming there is an ellipse or something like that, is strictly convex. Okay, so here, what is a convex body? And the definition of convex body, I didn't know it, the details here, but what people refer to body, it means the following. It means that you are convex, of course, compact. There is nothing, a lot of theorems require care with this. You can have an infinite, like the whole space, the whole Euclidean space is of course convex. And sometimes you have open ones like the upper half, space will be also convex. And sometimes we don't want these examples. We want them to be closed and bounded, in other words, compact, and with non-empty interior. So in other words, we want them to be full dimensional. So when we say a convex body in R3, which is why in this example, I artificially made this guy, I had this pentagon and I said, let's make it into a pyramid that was not of no consequence. I just wanted to be like a non-empty topological interior. It really means that you are like in your interior, your dimension is D. The affine span of the interior is the full space. So when we say convex body, we really mean these conditions. Convex, of course, compact. This really saves a lot of like strange situations. And we are going to we are going to really ask for this thing to have non-empty interior. In other words, if we are in our D, we want objects that have dimension D. We don't want to consider a segment, for example. A segment will be convex, and compact, but we will not have a non-empty topological interior. Okay, so now we have, okay, this will be used in a second. We are talking about convex bodies. And here we need another super important notion, which is in dimension 2, I have disjoint in order for my theorem to work, 4 tangents to 2 disjoint circles. In the example that we saw above, disjoint was not like a good thing. If I had 3 disjoint bodies, I could have any number of tangent hyperplanes. So I'm not going to talk about disjoint. I'm going to talk about another property called strongly separated. So this is very important. So this is what's called a strongly separated family. Okay. So what is the definition here? And there are several definitions in the literature. Like to me, the most intuitive one is this one. So for any subset, but that is non-empty and not the whole thing, I can separate. This is a, I could say the convex, but let me just say that this is a set, Ki, Kj, J in J. So I have the union of them, which is not convex. I could take the convex whole, but just as a set. This thing should be, we should be able to separate with a hyperplane, a strict separation. I'm going to ask for a strict separation from the other bodies. In the complement. Okay, so in any splitting that I have of my bodies, I can take 3 of them and the rest, and these bodies should be able to be strictly separated with a hyperplane. Okay, a strict separation, I mean, but this, I mean, there is a hyperplane in which that do not touch any of these 2 sets, and one of them is contained on one side and the other one is contained on the other side, and there is nothing. Strict means that you are not touching anything. Okay, so here the idea will be that if you have something like as a basic example, if you have 3 circles or anything like a square, a triangle, and something like this, a strict separation is asking that for any subset, so say these 2, I can separate any, well, in this case 3, so it's only the only possibility to split is 1 and 2. For any one, I can split it from the rest. Okay. So sometimes this is not doable. So, for example, something that I don't want to have is something like, I mean, you can imagine 2 circles, or let's say 3 circles. Something like this. Well, anyways, you can have a situation in which you have no strict separation. Well, without going further, I'm not. This is similar in dimension 2. This is similar to when I really mean that they are disjoint. They have to be disjoint. Like if you have the silly example will be in R2, I have 2 circles that are tangent here. If they are tangent in some point externally, there is only one way to separate one from the other, but this one will not be a strict separation, right? Because for a strict separation, I need this line to be disjoint from them, and in this case, the only way to separate is to touch them. So this will be not a strict separation. So this guy, again, in examples, this family, these 3 guys are strongly separated, and these 2 things are not strongly separated. So this is what we want to generalize. Instead of having 2 disjoint circles, I want to say, now I have convex bodies in RD, and I want them to be strongly separated. There is some restriction when you think about this, and it's that this M cannot be too large. Okay, without going further, in dimension 2, you cannot have 4 bodies that are all that are strongly separated, that you can split all possibilities. So this automatically puts a restriction. M has to be at most D+1. Okay, if not, it's simply not possible to have this condition. So M can be at most as large as D plus 1, although in our case, we're going to focus in M being between 1 and D. D plus 1 is a special case, and we have something to say about that. But in the more than that, it just simply is impossible to have a strongly separated family. Just think that you cannot have, I mean, forget about convex bodies. If all of these guys are points, you cannot have D plus 2 or more points that are strongly separated. Okay, so what is the theorem? So now this is the theorem. This is our main theorem of the paper. Let me put it in pink. No, this pink is ugly. Let me leave it like that. So this is, we have the family of strongly separated convex bodies. So I should put it here. Strongly separated, and remark here that we are talking about convex bodies. So I have some family, not just disjoint, but strongly separated. And now we can talk about the set of all tangent hyperplanes. And when I say tangent, in this case, I mean, and they have the family on the same side. Okay, so this thing, if we go to this example, I mean tangent lines, but I want to restrict my attention on the lines that have the family, in this case, the two circles on the same side. This is not an example because this is on one opposite side. So in this case, there are only two. This has both of them on the same side, and these have both of them on the same side. So we're looking at the common tangents with all of the family on the same side. This is not really a big deal. I mean, this is not really a big deal, as we will see, but for this statement, I want all of them to be on the same side. And this set, what we are going to denote TK, so tangents to the family K, is homeomorphic to a sphere, and this sphere will be S, D minus M. Okay, so the space of all tangent hyperplanes, this thing lives inside. So all hyperplanes, affine hyperplane, they don't have to go through the origin. If we are in RD, so everything here is in RD. Let's say that we are in a Euclidean space. Oops, let me put it in a bolder. If we are in a Euclidean space, everything happening inside RD, that's the D that every convex body is there, is full dimensional, so they all have dimension D. And here we are talking about M smaller than D, so I have to put it also maybe as a condition. And here M is smaller or equal than D, in order for this to be true. In this case, I want to remark that the space of all hyperplanes, this, I mean, when we say that something is homeomorphic, it has some topology. Of course, this space, these hyperplanes have a topology. They live in the projective space D in this case, because you have an equation, so you have D parameters for the equation, but is not going to zero. So you have an extra parameter for like your whole equation is like D and equal to something. So you have D plus 1 parameters, and we don't care about the scalar. So this is like a real projective space. So inside that space, we can talk about topology. So this is a subset, the tangent hyperplanes. They live here, so they have inherit a topology, and this topology will be homeomorphic to S, a sphere of dimension D minus M. This is the most general version. Let's try to see special cases. What happens is M is equal to D. So if M is equal to D, this thing is saying that is homeomorphic to S0. What S0 is 2 points. So what this statement is saying is that if you have D, so if you have 4 convex bodies strongly separated in R4, then they will have 2 tangent hyperplanes. So there are 2, specifically 2. There's not topology, discrete topology, and they informally they have to sandwich the family. So you have your convex meatballs, and then you have like a bread on top, a bread on the bottom. They don't have to be spheres, so they don't have to be strictly convex. They can be anything. In particular, they can be polytopes, and this is an example. We have 3 polytopes, and we can sandwich the family with exactly 2 hyperplanes. And this makes a lot of sense when you think about it. When you really think about it in dimension 3 concretely, you have 3 things, 3 meatballs. They are separated to avoid the crazy example that I show you later. So they behave like a triangle. So you have 3 guys that are like separated. Of course, you can put some floor and some ceiling, and that makes sense. And this is the case where D is equal to M. If M is smaller than D, then you will have more stuff. So let's think in general what will happen, like waving our hands with two bodies. If you have two convex bodies, let's say in R3, you have two balls. What is the space of all tangent hyperplanes? This thing is saying that it will be like an S1. It makes sense. If you have two convex bodies, the tangents are going to be surrounding. Okay, that makes also intuitive sense. And this should be true for two convex bodies in any dimension. So this is the general theorem. And what is the, how did we arrive here? What is the story of this statement? This statement looks or sounds true. So you wonder, well, maybe is this known? Do we have to wait, is it 2022 to learn this fact? And so looking at the literature, we found that a while ago in 1994, in a paper by, there's a lot of authors, so Cappell, Goodman, Pach, Pollack, Sharir, and Wenger. It's one paper with all of these authors. And they prove a statement like this, but in their proof, the convex bodies have to be strict. Okay, so they prove it for, say, spheres, balls, ellipses, and so they prove exactly this statement, but for them, strongly separated, strictly convex bodies. That's what they prove. So in their paper, they do not. So their methods really require being strictly convex. They really need that the tangents to be unique. In the paper, they speculate. They say, well, our proof doesn't work in the other. We don't know how to fix the proof, but it has to be true in general. We guess we don't see why not. It's just an artifice of the proof, and yeah, we think it's true in general. But also they don't really care because that's only one theorem that was a step in proving more stuff. So they used the theorem later to estimate something about common transversals. This paper is called, let me put the name, Common Transversals and Common Tangents. Oops. So they had several nice results there, and this theorem is just one step. So it seems to me that they didn't think too much about this. And they say, we can prove it like this. It may be true in general, but I don't know. And they kept going. Now, another version of this theorem was proven by Bisztriczky before them, and actually they reproved Bisztriczky. And Bisztriczky says, and this is the true generalization of the Greek problem. He says, okay, give me a family of strongly separated D-convex bodies in RD. So 2 circles in R2, 3 spheres in R3, 4 spheres in R4, and so on. And they have to be strongly separated. So any subset can be strictly separated from the rest. Okay, if that's true, then there are 2 to the D common tangents, which is the generalization of the 4 tangents in dimension 2. In the case of the polytopes here, you can think, well, there are 2 that puts all of them on the same side. But then there are 6 more depending on which one they isolate. So in this case, there are 2 more that isolate this one versus the other 2. So there are 2 tangent hyperplanes to the common tangents. So 2 hyperplanes, the blue and this one, that are tangent to all of them. But now they don't have all of them on the same side, but they are isolating this pyramid from these 2 in 2 ways. And when you think about it, you can make the drawing and you can find 8 of them. So depending on which one you want to isolate, you can find 2. So there are 3 options for the isolation, that's 6. And the two ones that have the whole family on the one side, those are 8, and that's it. In Bisztriczky theorem, he has it for convex bodies. General convex bodies, he doesn't ask them to be strict. So his proof, well, I'll talk about his proof in a second, but in this paper, they proved our general statement when is strict and the rest of the statement. But in the case where n is equal to d, they can remove the strict condition. They say, well, in that particular case, we can prove that it works for all convex bodies. And they use that to give an alternative proof of Bisztriczky. This is very similar to our statement, because don't get distracted by the 2 to the d. This is not really a problem. The really hard part is that there are 2 that has everyone on one side. Once you have 2 that sandwich the family, then you start playing with some signs to like move them around the hyperplanes. And it's not really that hard to go from 2, the 2 separating to the d. So I will say that really what this theorem is talking about is the case m equals d. When you have b convex bodies in our d, there are 2, that's the core. There are 2 tangent hyperplanes, common tangents that have the whole family on one side, that they sandwich the family. Once you have those 2, you can play and get to this 2D. That's not really a big deal. So the case m equals d had at this point 2 proofs, one by Bisztriczky, and they also prove it in general, because they can remove the strict convex condition in that case. So these 2 proofs, they do induction. The idea in these 2 proofs that they do induction, they try to say, well, let's try to, I have 3 bodies and somehow I want to delete one body. And they deal with that somehow. This is the strategy of Bisztriczky, and this is also the strategy of this paper. They do induction by deleting one body and going on with that. Okay, so let me go back to our statement. This is all I want to, this is the one thing that I want to say today. This is the statement. So let me read it again. I have a strongly separated family of, it can be any number of convex bodies less than d. And the set of all tangent hyperplanes is homeomorphic to a sphere or of certain dimension. Okay, this is the statement that we can prove, more general than Bisztriczky, more general than the other. Right. How do we prove it? So I will just briefly mention what is the idea and what is the tool. So the proof has one idea and one technical lemma. So the idea is the following. Instead of doing, we are going to do induction also, but we find that it's more natural to do the induction in a dual problem. If I have three objects like this, we consider the convex hull of them. Okay, and in the convex hull, this is all full dimensional. I can assume that the origin is in the interior. I take the polar, and in the polar, I start coloring the boundary of the polar according to the color that it maximizes. If you think of this being a polytope, imagine that this thing is a polytope, this thing is a polytope, this thing is a polytope. So I have colors, I have 3 types of colors. When I take the convex hull, I get a polytope. Vertices have different colors. What we are looking at in that polytope is 2 facets that are rainbow, 2 facets that touch a vertex of each color. So if you go to the polar, we are looking for each vertex now become a facet, and we have a natural color. So there will be facets of blue color, facets of orange color, and facets of pink color. And instead of looking in the dual, now we are looking for a single point that lies on 3 facets, rather than a facet that has the 3 vertices. So we go to the dual, and we end up having something like this. So we will have a convex body, a single convex body, and its boundary will be color. So here I have my 3 bodies. Now I have one convex body that has is covered with 3 things, something blue, something orange, something pink. And I want to prove that there are, in this case 2, I'm looking for rainbow points that are contained in these regions, in the closure of these 3 regions. Okay. So we are looking for rainbow points. And at this point, you may wonder, well, let's skip the line and say, well, if I have SD covered with D things that are convex, that are homeomorphic to balls. So there is one statement that one is tempted to say, well, if I have SD covered, by the way, you can prove that each color is homeomorphic to a ball. So SD covered with D balls. Is it true that the intersection of all of them is 2 points? So this one is tempted to say, okay, I finish. I just covered, this looks like some borsuk-ulam or something like that. It looks like I have SD covered with D balls. If you think about it, in dimension 2 is true. You have S, no, I have SD plus 1. So you have S1 covered with 2 segments, and they are both segments. They have to intersect into points. Well, it's obviously true. In dimension 3, you think about it, and yeah, it looks true. But then you go to dimension 4, and this is not true. You can cover S4 with 4 balls, and the intersection may be empty. I mean, it's not true because the intersection might be empty. So I cannot just simply say, I cannot simply finish the problem here. One has to remember that this coloring has certain properties. And the properties is that these colors that I have, the way I'm coloring my ball, so if this was a polytope, I get in the polar, I get my facets color. These colors are not just homeomorphic to a ball, but basically the strong separation is giving me more. A strong separation implies that the colors that I'm using in the dual, not just the colors, but any set of colors is visible and co-visible. Well, any proper set of colors is visible or co-visible. And this is key. So this is like, they are some sort of like convex thing. Meaning that it's not just that they are homeomorphic to a ball, it's that there exists a point that if you look at my object, it's seeing exactly that region. So this put more restriction. It's not just, I'm not just covering with balls. It's not just, it's a topological ball, but it has more restriction. It has to be, that region has to be visible from a point. And visible is what you think it is. Or co-visible, meaning that the complement is visible. Okay, so the idea is we take this problem, we dualize it. So now we are covering, we have a problem if we have a convex body covered with certain regions, and these regions are visible or co-visible, and we are looking for rainbow points. Okay, so now we do induction. This is the idea of the proof, is we do induction. Because in dimension 3, for example, I try to make this cartoon here. So we have 3 colors corresponding to our original 3 convex bodies. So I have 3 convex bodies. In the polar, I take the convex hull and take the polar. In the polar, I have colors from the boundary. So in my boundary, I have 3 colors. But I'm saying that each of the colors must be visible. What does it mean? It means that there is a point here that all that it sees from this body is the pink color. Now, if all that it sees is the pink color, then you can do some projection and project to some convex body in which this is the pink one. So I forget about it, that's the interior. And this boundary with the blue, I color it with blue. And this boundary with the orange, I color it with the orange. So in this way of doing induction, I can lower the dimension and I can forget about one of these colors because this color now become the interior of this and I don't care. So I will just only care about the boundary and I'm looking for rainbow points in the boundary, which will correspond to the rainbow points in this thing. So that's the idea. That's the $1 million idea. We also do induction, but we do induction in the dual by taking one color because it is visible. We take advantage of the fact that we have a point of visibility. When we have a point of visibility, that literally means that I can cut it here and lower the dimension because this will be 1 dimension lower and my body will have 1 color less. Okay, that's the idea. And that's how we prove it, because then we start removing 1 color at the time until you get to 1 color. When you go to 1 color, the problem is pretty simple. So you have 1 convex body. What is the space of all common tangents? Well, S to the d minus 1 if you have dimension d, because for any direction there is a common, for any direction in the sphere, there is a unique common tangent. So if we start lowering it, the dimension until m is equal to 1, we're done. Now, we're not really done because there are a lot of annoying details here. And the technical parts of this took us quite a while. The induction step, you have to verify a lot of things. So there is this step. You need to verify that everything really goes down. That if this color is, I mean, we need to use the fact that this set is visible because a strong separation said not just that each color, but each proper union of colors is visible. So we need that the visibility of these two things implies the visibility of this color, so that we are still on the same condition. That inductive step makes sense. Okay, we can deal with that. But there is another technical lemma, like difficult technical lemma, I think, and we import it from another paper. So this is, we use something, because by the way, we are talking about homeomorphism from this boundary to this boundary, and that sounds true, but it's very hard to prove. Well, I found it hard to prove. So we use a theorem from Ewald, Larman, and Rogers. Okay, so this theorem says the following: you have a convex body and H a generic, and I need to highlight generic. A generic hyperplane, and this is the orthogonal projection. Wait. Okay, so I take any convex body, really any convex body, then I take a generic hyperplane that is any generic hyperplane, and this induces an homeomorphism. This is what we need. The fact that it induces an homeomorphism between the boundary of the image and the pre-image. What the hell? So let's do a picture. So I have my convex body here. This is my convex body is in blue. So this is the convex body. I take any hyperplane. So this is the hyperplane in green. This is the hyperplane. And now I do a generic projection. So I project, and well, the projection of a convex body is a convex body. Okay, so I end up having some, this is the projection, this is pi k. Let's put the example in which you have a sphere and it goes to a circle. So this is the projection, the whole thing. Now, what this thing is saying, what they say is that if H is generic, there is an homeomorphism between this boundary, which is a circle, to the pre-image. Okay, this sounds very reasonable, but this is not always true. Okay, let's give an example of what can go wrong. So it can go wrong that you have a square, you project to a line, and if you project to a line, your image, this is your pi going down, your image is a segment. Now the segment has, the boundary has just 2 points, and these 2 points, this thing is not inducing an homeomorphism between these 2 points and their pre-images. Okay, that can go wrong. But you can see that in this example, clearly, there are 2 special directions in which this cannot happen. Generically, it's always going to be the case that this thing, generically, if I do another projection, it will be the case that at the end, I will project onto something like this, and it will be homeomorphic to 2 points. So this is why this is important. This theorem is really a consequence. So if you are familiar with this, what they prove is more specific. It's like, let's say that when this is not true, this is like a bad direction. And in the sphere, so you can have the unit sphere of all direction for hyperplanes, and they say something like projections. They can quantify the bad directions, and they can say that these have certain Hausdorff dimension inside the sphere. In particular, it has measure 0. In particular, generically, you're fine. So the bad directions are very small. So that's really not important. So this theorem is doing a lot. And how to prove this thing? There is a generalization by Salgaler. There is nothing special about projecting to a hyperplane. You can project to any linear subspace, and there is a version by Salgaler doing precisely that. So this theorem in Rolf Schneider's book is like 6 pages, very technical. It's one of these things that sounds reasonable. It is true, but the proof is harder than what you imagine. And this is exactly what we want. So in this case, we're having orthogonal projections, and this is not an orthogonal projection, but it is, if you cheat a little bit and you say, well, do a projective transformation and send this point to infinity, this projection into the visibility region becomes an orthogonal projection onto a hyperplane. Okay, So this is the technical lemma that allow us, a fundamental piece that allow us to go down, keeping the homeomorphism and the genericity of this thing. One has to be very careful about. So that means that in order for this to be true, this point we should be able to take it generically. So we also have to review all of the steps and be always sure that we can choose everything to be generic, which is tricky, but these details are annoying and I'm not going to bother you with all of it. So the idea is we do induction, and this induction is reducing the colors by 1. And one technical result that we import to do the induction is this thing that generically the visibility point allow me to bring the visibility region has some boundary, and that boundary we bring it homeomorphically to the new projection. And that is the main tool. Together with more analysis, we finish the proof of this theorem by reducing it to the case n equals 1, which is easy or trivial. Okay, so that's the idea of the proof. To finish in my last 4 minutes, I want to talk about some further directions, and this is something that I'm not very familiar with. But when I okay, so if you look at the original Greek problem, it's very innocent, it's very cute, it's 2,000 years old. You have 2 circles and you have to draw 4 tangents, and you can do it with an algorithm. Oh, I should say that if everything is a polytope, you can do it algorithmically too, which is important in keeping the analogy with the Greeks. But one analogy that I just said that I just say it without further consequence is, instead of having a circle, I'm going to have a convex body. So my generalization of their circle is an ellipse or a polytope or anything else in higher dimension. And there is another generalization, and I guess people like more in the MPI love this direction, which is instead of looking at the circle as a circle, think of it as quadrics in Rn. So replace the circle by a quadric. It may not be compact, it can be infinite, but replace it by a quadric and start looking at tangents, simultaneous tangents to all of these quadrics. This becomes a problem in a Grassmannian, and this is sort of well understood. But the tricky part, and to make it more similar to the Greeks, we would like them to be real. So there is a paper by Frank, there are several papers around this topic, but the most recent one that I found by Frank Sotilia, Torsten Theobald, called real K-flats tangent to quadrics in Rn. So in this case, they are trying to look for, instead of circles, they are quadrics, and they may be infinite, but never mind. And now they're looking for real K-flats that are tangent. There is another paper treating the case of lines tangent to quadrics. I think there are papers on specifically on spheres. So you need to find the right number of spheres. I think it's 2n minus 2 in Rn in order for the number of lines to become finite or something like that. But this is an open question. I know very little of this. So my generalization was convex bodies and tangent hyperplanes. But how about tangent K-planes? How can we say something about that? I give you 2 convex bodies, and now instead of looking at all hyperplanes, what about the set of all tangent lines? For example, if you have 3 of them, there are 2 tangent hyperplanes, all of them on the same side, but there are no tangent lines. Okay, and if you have 2, then there is like a whole pencil of lines that are tangent to both of them. I don't know. This is as far as I know, there is 0 work on this. There is some work on the geometric question, and the geometric question is talking about quadrics, and there is a lot of technology there because you can talk about intersection theory in the Grassmannian. But things that happen in, like, how they call it, like convex algebraic geometry, real convex algebraic geometry, are similar to convex geometry, but not quite. For them, for example, some solutions are either 2 to the n or infinite. Like, there is a point in which if you have too many, you need to have infinite. And here we could make an example, kind of artificial, but we could make an example having as many tangents, finitely many tangents. So we could have an object that is algebraic, not quite algebraic. I mean, any polytope is algebraic, but with a very large degree. So maybe there is something about the degree, it's not a quadric. And here, and I can have any number of tangents. So I don't know. So this is something to keep in mind. What is what can we say about tangent K-planes? In particular, I will be very interested about tangent lines. What is the space of all lines tangent to the bodies? Have no idea. And keep in mind that there is already some work when you replace it by quadrics. Maybe there is no need to replace by quadrics by any sort of like, maybe here we can put any degree, because a polytope, I don't know, I'm speculating here. So this is all I wanted to say. Let me just give you a big thank you.
All right, thank you very much. Are there any questions?
Can I ask a little random question?
Yes.
Okay, so you're discussing these tangent hyperplanes. Like, is there anything you can say about, like, let's say you have a hyperplane, you can sort of sometimes give it like a direction, and do you know anything about like possible signs of like what sides of the hyperplanes the convex bodies can be on?
What sides of the convex body of the tangent?
Yeah.
So right. So in general, we want all of them to be on one side. Okay. If that's in all of what I say, I want all of them on one side.
Okay.
But in the main theorem, all of them on the same side.
Right. Yeah. I was wondering if there's like a variation for.
But dealing with different sides is not that bad. This is the, for example, here you can imagine. This is not really true, but imagine that these guys, instead of being, imagine that they are all cones, and this is all goes to linear. Then negating a body can switches the, you can start using like the negative, apply the theorem, and then go back with the negative.
Yeah, all right.
Something like that. So it's not that bad to start playing with the sides.
Okay.
I would think that the hardest thing is to have them all on the same side.
Okay.
Now you make me wonder, in a line, if I need a line tangent, the line doesn't have sides. So I don't know. I think it will be better to maybe keep in mind that and just consider all tangents at the same time.
Okay. Thanks.
Any other questions? So the last problem that you said with the tangent lines, in my head now I have two kind of balls in R3 and I look at the tangent lines. Somehow my intuition tells me that this should be a torus. Is my intuition completely wrong?
No.
Or?
No, I mean, I don't know. We are on the after hours here.
Sure.
So if you have two, I think it's just like it's a surface. It's like a double rule surface. I mean, you can imagine, but it's a torus. No, I will say it's like a surface that is. It's a cool surface, I will say, but.
So in my head, you have like a circle's worth of possible tangents.
No, you're right. And also it can be like this. Man, I don't know. Yeah, good point. What is it in that case?
Yeah, I mean, all of a sudden, on one side, on the other side is you have to consider.
Sure.
Right, that restriction falls away. Is the issue.
You can put it here. You can put it here.
Yeah. Where those are strictly new from the hyperplane situation, right?
Yeah, I don't know.
Because that wouldn't be, because now you no longer have a hyperplane that contains that line that would fulfill the requirements of the previous theorem.
That's it. I don't know.
And
I don't know. And the important thing is that nobody knows. So go on, speculate, and we can write about it.
I'll speculate.
Fair enough. And you said about the tangent K-planes, was there partial results known already by people, or does that then really go into the quadratic?
If you have a smaller m, say 4 in R10, there was a result known, but what they proved is that they prove exactly the statement, but they need a strict convexity. So they had it for spheres. So strict convexity means that any tangent hyperplane is tangent in a unique point. So they have it for strict convex bodies. Their proof, if this
have
paper is very interesting.
Lower dimensional case, the
lower dimensional, lower amount, but only for strict. And they use some idea of cobordism. I think they use, cool tools, but they're a bit fancier. Our tools are more humble and more direct and simpler in a way. I mean, there are all important details, but when they are doing this cobordism, at some point they need to glue something, and this gluing requires this thing to be unique. That's why they say, like, we don't know how to do it in general, but it's because of our proof. It's not because we think it's not true. So that's their methods are different.
Fewer bodies or lower dimensional planes?
No. Fewer bodies. No, lower dimension.
Okay. Yeah, that's what I thought.
People don't like to deal with lower dimension because then you can be contained on a hyperplane.
Yeah.
I mean, you can say something about that, but it's a little silly. Yeah, so they had not lower dimensional, they had fewer bodies. Lower dimensional, I don't know. I don't think it's that different. We have a couple of lemmas like that in the paper, but it's just, we don't want to deal. So for example, in this statement, in Bisztriczky, you need to have, I mean, you are avoiding silly things. Like for example, if you have this square and a point, so you will, instead of having 4 tangents, you just have 2 tangents. It's just because in this tangent, you cannot say if this guy is on one side or the other side. It's simultaneously on both sides. So I think something similar will happen. Will be at most to the, just that these things cannot, you will not be able to distinguish them, something like that. I don't think that lower dimension is interesting. It's more interesting fewer number of bodies.
Sorry, I wasn't clear. I meant the planes being the lower on the lower.
No. That I don't know. I have no idea.
Yeah.
I mean, I only know in the algebraic case. For convex bodies, yeah. I don't know. And even the case of lines looks interesting and very unexplored.
Yeah. Is there an intersection in the, I mean, this is a philosophical question, but is there a decent intersection in the methods between the more algebraic cases and your cases? I mean, you already alluded to going all the way to intersection theory, so then it's then it becomes fun and powerful, but rather different.
I don't know. I mean, in my current understanding of the world, in my current epistemological sphere, I will say no. But maybe there is a deep relation inside, because you argue to intersection theory in the Grassmannian. Oh, by the way, what they do, I will say. So here they say, if you have the right number of quadrics in Rn, it has to be certain number depending on n and on k. Then there is a finite number of k flats that are tangent. Okay, but these arguments are over the complex numbers. So the Grassmannian gives you some genericity condition and say this intersection is over the complex numbers. So even when you know that this paper, the difficult part is the real part. You have to make them all real, and that's really. I mean, Grassmannian can only take you so far, give you an idea, but then you have to sit down and try to make it real.
All right. Are there any other questions or comments? Discussion points? That doesn't seem to be the case. So let's all thank Federico again for the nice talk.
Thank you all for
coming. Great discussion.